Hello friends, hope all of you are doing good. Today we'll see our remaining syllabus of Geotech Engineering Part 2. Before this Corona tragedy and lockdown, we have started our unit number 6, Stability of Slopes, and we have covered it 50%. Today we'll see the remaining points from this part. And it starts with this point called Swedish circle method. Now all of you know what we are dealing here in stability of slopes. We are dealing with safety of slopes. That means we are deciding the given slope is safe and stable or not. Is it safe? Is it stable? That we are going to decide over here. Already we have seen the Taylor stability number, we have seen the friction circle method, which gives you the factor of safety. But today we'll see this new method, the Swedish circle method, which is a graphical method to analyze a slope. Remember, to analyze a slope means to find out its factor of safety, to decide if the given slope is safe or not. Okay, let us quickly see what this Swedish circle method is. For example, say this is a slope I have, and slope is given to me, and I have to suggest is this slope is stable or not. The soil properties C and phi will be given to me, and I have to answer this slope is stable or not. That means what is the factor of safety for this slope. Okay. As always, we have to consider a trial failure surface. Let us consider this AB as a circular trial failure surface with the radius R. Trial failure surface means we are assuming the slope will fail from this particular plane of failure. That means everything will be moved from this particular circular face. Now this is just trial. We have to take number of such surfaces and we have to find out factor of safeties. Then we'll come to know the slope is stable or not. For first trial, let us see what to do. Make number of strips of equal width like this. This is a these are the strips we have. Now consider any one strip out of this. Give number to these strips 1, 2, 3, 4, 5, 6, 7, 8. Consider strip number 6. Okay. Method is somewhat tricky, different than friction circle method. What we are doing, we are just assuming this AB as trial failure surface. Then we have divided the part of that particular slope, that is failure part, we have divided into number of strips. Now consider any one strip. I am considering this strip number 6. What will be the forces in this particular strip number 6, obviously you will have self weight, then you will have the cohesive force, then you will have a reaction of soil R. So W, C and R are primary forces here in this particular equilibrium. Now there will be some boundary forces between the surfaces of the two successive strips, but those gets vanished because they are opposite to each other. So boundary vertical forces will be cancelled. Now in this particular strip number 6, I have involvement of these forces. Now first, that is my self weight of this particular strip W. Then I will have a cohesive force C, like this. This is my cohesive force C. Then obviously I will have a reaction from bottom. I will show it in upward direction. Reaction from bottom. That reaction will be at an angle of phi, like this. From this point you will have a radius this is your R. So to this R you will be having a reaction from soil like this. I will show you. Just a minute. This is my R. This is at angle phi to the radius from that point I am considering. Okay, so this is my R, this is W and this is C. So in this particular scenario, I have to find out two more components. I have to find out normal and tangential component of this W. How to find out normal and tangential component? Suppose this is your point of consideration. Draw a normal to that surface. Obviously this normal will be at angle phi. We have seen what is that angle phi earlier. So this is your normal component. Also find out what is the tangential component T. So with respect to W, we can draw that triangle. This is W. This is normal component at angle phi, and this is tangential component. So you have normal and tangential component. Obviously this normal component will be what? W into cos alpha, and tangential component will be W into sin alpha. So for this particular surface, what we need to find out? We need to find out normal component, we need to find out tangential component, then we need to find out what is C. C you will get from experiment what is C for given soil. So C value you will have. Then you can find out what is length of arc in this particular slip number 6. It is called as a slips or a strip. So what is the length of arc in that particular region of slip number 6? It is called as LA. Now these are the points you have. Also you can find out total length of this particular surface AB. It is also expressed as LA. This is the part you have done for only slip number 6. C will be same throughout all the slips because soil will be same. So cohesion value will be same for all the strips. You have to find out weight of all strips. Then once you know the weight, you will get normal component. Then you will get tangential component. So at last what you have for one slip or one strip, strip number 6, you have normal component, tangential component, you have C value. Likewise, find out the normal and tangential components for all of them. For all strips, find out what is normal component and what is tangential component and make the summation of those normal components and tangential components. C is common. Total length of slip surface AB you can find out. So you have these particular factors. Now next point is to find out the factor of safety of this particular slope. How we will get factor of safety? Already we have the basic principle or basic concept of factor of safety that everybody knows. It is a ratio of the resisting force to disturbing force or resisting moment to disturbing moment. If this disturbing moment is higher than resisting force, obviously factor of safety will be less than 1. Your slope will fail or your any structure will fail. Preferably what we want, this resisting force should be higher than your disturbing force so that your factor of safety will be more than 1. As your factor of safety increases, the safety of slope obviously increases. But that increment in factor of safety is dependent on this resisting force. Okay. Your aim is to improve the soil, improve the slope dimensions so that resisting force should be much higher than the disturbing force. Using that particular formula and these above values, what we can find out? We can find out factor of safety for this particular trial failure slope surface AB for the given slope. What this factor of safety will be? The factor of safety for this trial slope will be C into LA plus tan phi summation of all normal components of all strips divided by summation of tangential components. So this is your final formula to get factor of safety from Swedish circle method. Method is very easy. Take a surface, a trial failure surface, divide it in number of strips, find out its weight, find out normal and tangential component, find out cohesion value and length of that particular AB surface. Then repeat the procedure for all the strips and find out summation of normal components, summation of tangential components. Ultimately you will get this factor of safety formula. Okay, this is a graphical method to analyze a slope which will give you the factor of safety. If factor of safety is less than 1, slope is in danger. If it is far more than 1 or it is more than 1, it is safer. Okay, let us consider one problem from your previous question papers. This is a problem we have. This is asked for 8 marks in April 2016. Stability analysis by Swedish circle method gave following values per running meter for 10-meter high embankment. Embankment is nothing but a slope. All of us knows that. Then they have given you the total shearing force, total normal force, total neutral force, then length of arc. Next line they have mentioned, if the properties of soil are C equals to 24, phi equals to 6 degrees, calculate factor of safety with respect to shear strength. So read the problem carefully. They have given you shearing forces, normal forces, neutral forces and length of arc. They have given you the value of C, value of phi. Ultimately we have to find out factor of safety with respect to shear. Let us write down the given data first. Total shearing force they have given you as 480, that means your tangential component, summation T, because they have mentioned total, that means they have given you the summation T. Then they have given you total normal force, that is summation N, summation of all normal components. They have given you this neutral force, we call it as X, or we can call it also as U. This is 250 kilonewton. Then they have given us the value of phi, value of C. Now we have the formula previously. That formula of factor of safety was C into L arc tan phi summation N divided by summation T. Now that formula will be varied because here they have given you total shearing force, total normal force, total neutral force. Neutral force means force that will reduce your disturbing moments. So what will be the change? A small or slight change in the formula will be C into L arc summation of normal components minus this U. This is your change in the formula. This U is your neutral force, tan phi divided by summation T. Put all the values, you will get factor of safety 1.47. So if that factor of safety value is more than 1, obviously your slope is stable. So in that way, by using this Swedish circle method, we can find out factor of safety for any slope. Now this is your trial surface AB. Take number of slip surfaces, find out factor of safety of each surface. you will get some minimum value, some maximum value. Minimum value you should consider for that stability of that particular slope. Okay, so in that way we can analyze the slope by using Swedish circle method. Today we'll stop here. Next time we'll see some new point. Take care. Thank you.